Math 2414, excuse me, not the right class. 2412 is calculus, and although we definitely need to know some calculus for this, this is Math 2414 calculus 2. All right, Math 2414, Trigonometric Substitutions 2. First look at a trig sub. In the previous video, we ran across this integral and tried the substitution u equals 1 minus x squared. I need this to draw. And then we took the du to get negative 2x dx. But the problem was our du package needed an x, and there was no x in front of the radical in this integral, and it created some issues. But this isn't the only substitution we could do. I kind of hinted in the previous video that we're going to make a trig substitution by taking advantage of the structure of the part under the square root, the 1 minus x squared. In other words, if we take 1 minus x squared and compare it to 1 minus sine squared of something, we'll say sine squared theta. If it looked like that, then we could use a trig identity to rewrite that as cosine squared. And being parked under a square root, the square would cancel the square under the right conditions of the theta, which we'll talk about briefly. But we're going to make this happen, and we need to figure out what change to make. Well, the easiest way to figure this out is just connect what we have with what we want. What we have is x squared. What we want is sine squared of theta. So we need x squared equal sine squared of theta, i.e. we need x equal sine theta, and that's the substitution we're going to make. It's called a trig substitution because we're substituting a trig function for a variable, and as a consequence, we're going to be able to make this thing integrable. Quick comment though, in order for substitutions to work, the function that we put in there has to satisfy some conditions, such as being 1-to-1, which means it has an inverse. But without worrying about that too much, we'll categorize that in a couple more videos. But keep in mind that there are technically some restrictions on what theta can equal. In this particular case, theta could be between negative pi over 2 and pi over 2. But again, we'll worry about that later. So based on the fact that 1 minus x squared has the same structure as 1 minus sine squared, we're going to make the substitution x equals sine squared theta. Let x equal sine theta. And then proceed like we normally would. Then dx, the derivative of x, well, the derivative of sine is cosine theta, d theta. And you may be worried because we need a cosine theta, but look a little bit more closely. This substitution, which is sometimes called a reverse substitution, says dx equals something. Well, here's the dx, and it's equal to all of this. So we don't have to worry about balancing a du, because this type of substitution where you say x equals something, it instantly tells you what dx equals. So let's make these substitutions and see what happens. Now, just to warn you, I am going to be drawing something down here in this space, a triangle to be exact, or to be more exact, but when the time is right, we'll do that. All right, so let's make these substitutions. We get the integral of the square root of 1 minus sine squared theta, and dx is equal to cosine theta okay, not a problem. Well, not a problem. We just changed it from an algebra integral to a trig integral, but we did it with a motivation in mind. The square root of 1 minus sine squared is going to simplify because 1 minus sine squared is equal to cosine squared. Grab this cosine out here. And assuming cosine of theta is positive, with the proper restrictions on theta it would be, the square and the square root flat out cancel, leaving the integral of cosine theta times itself. Oh, wait a minute, cosine theta times itself, we can just say the integral of cosine squared theta. And now we've turned it into a problem that we've experienced already. We have rules for integrating powers of sines and cosines, but specifically, if you're integrating an even power of cosine, you should use a power reducing identity, power reducing formula, if you will. Without reteaching everything from that video, cosine squared of theta equal to 1/2 plus 1/2 cosine of 2 theta. So we can change the integrand to that. 1/2 plus 1/2 cosine of 2 theta d theta. And at this point, the function is now integrable. If we integrate it, the integral of 1/2 d theta is 1/2 theta. The integral of cosine is negative sign, but here's where you have to be careful. And technically, we could do another u substitution here. We could say u equals 2 theta and play that game. But as I mentioned in previous videos, if you're going to do a substitution and the derivative of that substitution is constant, you can actually not do the substitution by staying focused. Just do the antiderivative like you normally would. The antiderivative of cosine, the antiderivative of cosine is positive sign, not negative sign. But the antiderivative of cosine is sine. But if we did a u substitution, we would have to balance the derivative of the inside with the reciprocal of the derivative of the inside. In other words, we pick up another 1/2 to go with the 1/2 that's out there, multiply it, and you get 1/4. Again, if that's too big of a leap for you, then please, please, please pause the video, go over here, excuse me, say u equals 2 theta, and then proceed with your standard substitution protocol. All right, so are we done? Well, yes and no. Yes, because we evaluated the integral, but no, because we have the wrong variable. When you do a substitution to evaluate an integral, you are expected to undo that substitution. There are exceptions when it's a definite integral, but this isn't, so no exceptions here. So how are we going to undo the substitution? Well, normally the way you undo a substitution is you replace the new variable with what it equals. Actually, we're going to do that here. There's one problem, though. We really don't know what theta equals. We know what sine of theta equals. We know that sine of theta is equal to x right here. Did not mean to erase. We know sine of theta is equal to x. So what do we do at this point? Well, let's move this over to the next page and I'll show you how to undo the substitution. All right, I've just brought over the substitution x equals sine theta and the point where we are so far in the integral, 1/2 theta plus 1/4 sine of 2 theta plus c. The trick to undoing a trig substitution is to draw a triangle of the substitution. But what do I mean by that? Well, assuming our angle is acute, meaning less than 90 degrees, and that's a safe assumption to make here, we can put that angle inside a right triangle. And now let's draw a picture so that sine of theta is equal to x. Keeping in mind that sine of theta by definition is opposite over hypotenuse, we need to draw this triangle so that opposite over hypotenuse is x. Well, the x isn't a fraction unless you put it over 1, and so we can draw this triangle with an opposite side of x and a hypotenuse of 1. That's a picture of sine of theta is equal to x. Now, how are we going to use that? Well, we need to figure out what to do with this theta and what to do with that theta. Actually, the first theta, we didn't need the triangle. I'm going to move the triangle if I can grab it and then slide it down without it being distorted. So give me 1 second here. There we go. Now, what do we know about theta? Well, we know that's its picture, but in that first theta, in our answer, we just need something to substitute for theta. We don't need cosine of theta, sine of theta, or anything like that. We just need erasing. We just need to know what this theta equals, flat out. So how are we going to do that? Well, it's real simple. Take our substitution and solve it for theta. And all you have to do to solve it for theta is to take the arc sine of both sides. If we took arc sine of both sides, we would get theta equals arc sine of x. The good news is we got something to substitute for theta. So let's go ahead and do that on the first part of our answer. Theta is equal to arc sine of x, or sine inverse if you prefer. But what are we going to do with the other theta? What are we going to do with the theta inside of 1/4 sine of 2 theta? Well, the problem with our picture, which by the way has a missing side, which we'll figure out in a moment. The problem with our picture is that our picture is for an angle of theta. Stop erasing. Our picture is for an angle of theta, but our trig function is a trig function of 2 theta. So our picture is not for that angle. So before we can use the picture to figure sine of 2 theta, we've got to rewrite sine of 2 theta without the 2. Well, this is where you have to be familiar with your formulas like double angle formulas. So for the sine of 2 theta, we are going to use a double angle formula. I'm going to write it just to remind you what it is, but then I'm going to erase it because it's going to be in the way. In the videos I created reviewing some trig identities, one of them was sine of 2 theta equals 2 sine theta cosine theta. You need to have that identity memorized. There's no way around it. Know it, because it will show up in situations like this. We can use that identity to rewrite sine of 2 theta as an expression of functions of theta by itself, and so our triangle will come. So let's replace the sine of 2 theta inside our answer with 2 sine theta cosine theta. And there we go. So what do we get from this? Well, first off, we get a 1/4 times 2, which will become a 1/2 on the next line. But more importantly, we get trig functions of theta, which our triangle can help us figure out. In fact, we know what sine of theta equals from our substitution. We know that sine of theta is going to equal x. That's just straight up from our substitution. Well, what is cosine of theta going to equal? Well, this is where our triangle can come into play. Cosine, of course, is adjacent over hypotenuse. We have a picture of theta over here. Problem? To find cosine, we need to know this missing side. So we would have to do a little bit of Pythagorean theorem, but I'm going to spare you the algebraic details because they are pretty simple. And plus, this technique was also demonstrated in the trig identity review videos. But the adjacent side here has to be the square root of 1 minus x squared. This happens to be the square root that was in the integral, not coincidentally. So based on that picture, I now know expressions that I can write for both sine and cosine. Well, I knew what I could write for sine at the beginning. That was our substitution. But the picture agrees with it. But according to this picture, what does cosine equal? Well, it's adjacent over hypotenuse. So it's the square root of 1 minus x squared over 1. So it's just the square root of 1 minus x squared. Let's write our final answer. 1/2 arc sine of x plus the 1/4 times 2 makes another 1/2. Sine of theta equals x. That our substitution blatantly says that. But according to our triangle, the cosine of theta is equal to the square root of 1 minus x squared. We have plus a constant, and that ends the problem. Now, was this a long, drawn-out approach? Of course it is. But don't worry, when the time is right, we'll categorize it.